February 22nd, 1945, 30 miles east of Aachen, Germany. The sound arrived first, a low-frequency hum that seemed to emanate from the earth itself, vibrating through the frozen ground and into the boots of every soldier standing near the mobile radar installation. Technical Sergeant Robert Chen pressed his headphones tighter against his ears, watching the phosphorescent sweep of the cathode ray tube as it painted green ghosts across the circular screen. Each revolution revealed the sky's invisible architecture: friendly aircraft returning from missions over the Ruhr, enemy fighters scrambling from airfields the Luftwaffe still desperately defended, and something else, something the Germans had not yet realized, was watching them with electronic eyes that penetrated clouds, darkness, and the very distance that had once provided sanctuary. The SCR-584 radar installation sat camouflaged beneath winter bare oak trees, its dish antenna rotating with mechanical precision, sending invisible pulses into the stratosphere and receiving echoes that transformed aircraft into mathematical coordinates. The equipment occupied 3 trucks networked by cables snaking through the mud, the antenna vehicle, the receiver transmitter van, and the power unit whose diesel generator provided the electricity that made omniscience possible. Around this technological nerve center, a platoon of soldiers maintained security, unaware that the humming machinery they guarded represented a revolution in warfare as profound as gunpowder or aviation itself. 20 miles to the east, Oberleutnant Friedrich Weber sat in the cockpit of his Focke-Wulf FW-190, scanning the afternoon sky with eyes trained to detect threats before they became lethal. He had survived 37 combat missions through a combination of situational awareness, aggressive tactics, and the veteran pilot's instinct for danger. He checked his 6 o'clock, cleared his blind spots, and maintained the scanning pattern that had kept him alive when so many others had died. What he could not see, what no amount of visual vigilance could detect, was the radar beam that had found his aircraft 3 minutes earlier, had measured his altitude, speed, and heading with mechanical precision, and had already transmitted this information to an American anti-aircraft battery that was now training its guns on coordinates where his aircraft would be in 45 seconds. The shell that destroyed Weber's FW-190 arrived without warning, exploding 20 meters from his aircraft with a violence that shredded control surfaces and punctured the fuel tank. He had no time to process what had happened, no opportunity to identify the threat before his fighter was tumbling through the sky, trailing smoke and flame. As he struggled with the canopy release, fighting G-forces and the aircraft's violent gyrations, Weber's final coherent thought was confusion. He had maintained perfect tactical awareness, had seen no enemy aircraft, had received no warning, yet death had found him with the precision of a sniper's bullet delivered from an invisible rifle. Chen watched the radar blip disappear from his screen, a brief notation in the mission log, the only evidence that a human being had just died because of information his equipment had provided. There was no celebration, no acknowledgement beyond the professional detachment required to continue working. The radar swept on, indifferent to individual fates, revealing other aircraft, other targets, other coordinates to be transmitted through the integrated air defense network that was systematically destroying what remained of the Luftwaffe's operational capacity. The hum continued, constant and hypnotic, the sound of electromagnetic dominance translated into audio frequency, the voice of a technology that had made the sky transparent and rendered obsolete every tactical doctrine developed during aviation's first 4 decades. This technological asymmetry, American radar superiority operating beyond German awareness or effective countermeasure, represented one of World War II's most decisive yet least visible advantages. It exemplified how industrial capacity, scientific innovation, and institutional competence combined to create military capabilities that transcended traditional measures of strength. The radar installation scattered across liberated Europe operating with systematic efficiency to detect and track aerial targets, embodied a transformation in warfare where information dominance became as important as firepower, where the ability to see the enemy before being seen determined outcomes before weapons were even fired. To understand the magnitude of this advantage, one must first grasp the state of radar technology and doctrine in the combatant nations. Radar, radio detection, and ranging had been developed in the 1930s nearly simultaneously by researchers in multiple countries including Britain, Germany, and the United States. The basic principle was simple. Radio waves transmitted toward a target would reflect back, and by measuring the time delay and characteristics of the reflected signal, one could determine the target's range, bearing, and other properties. But translating this principle into functional military systems required solving enormous technical challenges in electronics, signal processing, and operational integration. Britain had led initial military radar development, driven by desperate necessity as German air power threatened the home islands. The Chain-Home radar network, operational by 1939, provided early warning of Luftwaffe bomber raids and contributed decisively to RAF victory in the Battle of Britain. German engineers had also developed radar systems, including the Würzburg and Freya sets that provided air defense and fire control capabilities. But American entry into the war brought industrial and scientific resources that would transform radar from experimental technology into systematic military infrastructure. The MIT Radiation Laboratory, established in 1940, became the center of American radar development. The Rad Lab, as it was known, employed thousands of physicists, engineers, and technicians working on dozens of radar systems for different military applications. The research benefited from American industrial capacity that could translate laboratory prototypes into mass-produced equipment, from scientific talent drawn from universities nationwide, and from institutional commitment to systematic innovation. By 1945, American forces deployed radar systems whose sophistication and reliability exceeded anything available to Axis powers, creating information dominance that shaped every domain of military operations. The SCR-584 radar that Sergeant Chen operated represented the pinnacle of American mobile anti-aircraft radar development. Introduced in 1944, it incorporated advanced features including automatic tracking, precision sufficient for gun-laying fire control, and integration with computing systems that calculated firing solutions. The radar operated on 10-centimeter wavelength, using cavity magnetron technology that Britain had shared with the United States in 1940, a technology transfer that Churchill later called one of the most valuable contributions to Allied victory. The SCR-584 could detect aircraft at ranges exceeding 30 miles, track multiple targets simultaneously, and provide accuracy sufficient to direct anti-aircraft fire with lethal effectiveness. German radar development had followed different trajectories, shaped by Nazi Germany's institutional dysfunctions and resource constraints. German scientists understood radar principles and had developed operational systems, but German radar never achieved the systematic integration and mass production that characterized American deployment. Multiple competing research programs wasted resources on duplicative efforts. Production priorities favored aircraft and tanks over electronics. The Nazi regime's persecution of Jewish scientists and intellectuals had driven away or murdered many of Germany's most talented researchers. By 1944, German radar capabilities lagged years behind American and British systems, and the gap was widening. More fundamentally, German military doctrine had not adapted to radar's implications. The Luftwaffe understood radar as a defensive technology, useful for warning of enemy attacks, but peripheral to offensive operations that emphasized pilot skill and aircraft performance. German fighter tactics relied on visual detection and individual initiative, with pilots like Oberleutnant Weber employing techniques perfected over years of combat. These tactics had been effective when opposing forces operated under similar information constraints, when all pilots searched for enemies using biological vision with its inherent limitations. But radar transformed the information environment, making visible what had been invisible and providing comprehensive situational awareness that human senses could never achieve. Weber had been an exceptional pilot by any measure. He had trained at a Luftwaffe fighter school in 1942, had survived combat against Soviet, British, and American opponents, and had developed the situational awareness and tactical judgment that distinguished veterans from casualties. His survival through 37 missions represented skill, courage, and luck in measures that few possessed. He understood his FW-190 intimately, knew its strengths and limitations, and employed tactics that maximized advantages while minimizing exposure to enemy fire. What he could not understand, what no amount of tactical brilliance could overcome, was fighting an enemy who saw him before he saw them, who tracked his movements with electronic precision, and who directed fire using information he had no ability to detect or counter. The radar-directed anti-aircraft fire that killed Weber represented the integration of multiple technological systems into a network that transcended individual components. The SCR-584 radar provided detection and tracking. The M9 Director, an analog computer, calculated firing solutions based on target data, accounting for projectile ballistics, target motion, and atmospheric conditions. The 90mm anti-aircraft guns, positioned according to coverage requirements determined through systematic analysis, fired shells, fused to detonate at precisely calculated altitudes. The entire system operated with mechanical precision, processing information and executing fire missions faster than human cognition could manage. German pilots facing this integrated air defense network found themselves dying without understanding why. They maintained visual vigilance, employed defensive maneuvers, and followed tactical doctrines that had previously kept them alive, yet they were being shot down by anti-aircraft fire that seemed impossibly accurate. Some attributed it to luck, others to overwhelming American firepower, but few understood that they were fighting an enemy who possessed systematic information superiority that made German tactical skill increasingly irrelevant. The sky had become transparent to American observers while remaining opaque to German pilots who relied on vision that could not penetrate clouds, darkness, or the distances from which radar operated. The psychological impact of this invisible threat was devastating for Luftwaffe morale. Pilots could understand and adapt to visible dangers, enemy fighters, anti-aircraft fire they could see, ground threats they could identify, but radar-directed systems killed without warning, striking from ranges and angles that violated everything pilots understood about tactical geometry. The randomness, at least as pilots perceived it, created helplessness that eroded combat effectiveness even among survivors. Weber had been skilled and lucky for 37 missions, but the 38th mission encountered a system that made skill and luck insufficient protections against technology they could not perceive. Sergeant Chen, watching his radar screen in that camouflaged installation east of Aachen, embodied a different military culture. He was not a warrior in traditional terms. He had never fired a weapon in combat, would never engage in dogfighting or close-quarters battle, and possessed no martial skills beyond basic training. But he was a critical component of a military system that valued technical competence, systematic process, and information mastery. His training had emphasized electronics theory, equipment maintenance, radar operation procedures, and communication protocols. He had learned to interpret the phosphorescent traces on cathode ray tubes, to distinguish aircraft from ground clutter, to estimate altitude and heading from radar returns, and to transmit target information with the precision and brevity that military communications demanded. The installation Chen operated was part of a comprehensive air defense network that covered liberated Europe. Radar stations communicated through radio networks and telephone lines, sharing information that created a common operational picture extending across hundreds of miles. Fighter direction centers used this information to vector Allied fighters toward enemy aircraft. Anti-aircraft batteries received target data, allowing them to engage threats beyond visual range. Command centers tracked friendly and enemy air movements, coordinating defensive measures and identifying gaps in coverage. The entire network operated with systematic efficiency, processing thousands of aircraft movements daily, distinguishing friend from enemy through IFF transponders, and maintaining operational tempo that German forces could not match. The physical manifestation of this network, the radar installations, communication centers, command posts, and supporting infrastructure, represented American industrial capacity translated into military advantage. Each radar set required precision electronics manufactured to exacting specifications. Thousands of vacuum tubes, resistors, capacitors, and other components had to be produced reliably and assembled into functional systems. The power supplies, antenna mechanisms, and auxiliary equipment demanded machining, metalworking, and electrical engineering. Maintenance required trained technicians, spare parts logistics, and institutional knowledge about troubleshooting and repair. The entire system depended on supply chains, training programs, and organizational structures that could sustain complex technology under combat conditions. Germany could not replicate this achievement. By 1945, German industrial capacity was collapsing under Allied bombing, resource shortages, and systematic disruption of production networks. What industry remained prioritized weapons with immediate battlefield impact, tanks, artillery, ammunition, over sophisticated electronics with longer development cycles and more complex maintenance requirements. The institutional chaos of Nazi governance, with competing agencies pursuing duplicative efforts and political loyalty valued over technical competence, prevented the kind of systematic innovation that American institutions achieved. German radar remained inferior in performance, limited in deployment, and poorly integrated with other military systems. The strategic implications extended beyond individual tactical engagements. American radar dominance enabled air operations that would otherwise have been impossible or prohibitively costly. Heavy bombers conducting daylight raids over Germany navigated using radar when clouds obscured visual landmarks. Fighter escorts used radar-equipped night fighters to defend bomber streams against Luftwaffe interceptors. Ground forces advanced with confidence that air superiority was maintained through systematic detection and interception of enemy aircraft. The entire Allied strategic bombing campaign, controversial in its execution and impact, depended fundamentally on radar's enabling technologies. The sound that Sergeant Chen heard, that low-frequency hum of radar operation, became the signature of American technological dominance. Soldiers stationed near radar installations grew accustomed to it, incorporating it into the ambient soundscape of military operations. But for those who understood what it represented, the hum carried significance beyond its auditory properties. It was the sound of electromagnetic waves being generated, transmitted, and received. It was the sound of electricity transforming into information. It was the sound of American industrial civilization projecting power through scientific mastery and technical sophistication. Most fundamentally, it was the sound of asymmetric advantage. Americans possessed capabilities that Germans could detect only through their lethal effects, could understand only through catastrophic demonstration, and could counter only through defeat and occupation. German technical intelligence services attempted to understand Allied radar capabilities through captured equipment, interrogation of prisoners, and signal intelligence. They recognized that American radar performance exceeded their own systems, documented specific capabilities, and reported findings through military channels. But understanding the problem did not enable solutions. Germany lacked the industrial capacity to mass-produce equivalent systems, lacked the scientific personnel to rapidly develop improvements, and lacked the time required to translate research into operational deployment. The technological gap continued widening as American production and innovation accelerated while German capabilities stagnated or regressed. Some German efforts to counter radar achieved limited tactical success. Chaff, metallic strips dropped from aircraft to create false radar returns, could temporarily confuse radar systems. Radio jamming could disrupt communications and degrade radar performance. But these countermeasures required resources Germany could not spare, provided only temporary relief, and prompted American technical responses that restored effectiveness. The fundamental asymmetry remained unchanged. Americans possessed systematic information superiority that shaped operational planning and tactical execution across all domains. The human cost of this technological disparity manifested in deaths like Weber's. Skilled pilots killed by threats they could not see, shot down while maintaining tactical awareness that had previously meant survival, destroyed by systems that reduced aerial combat from test of skill and courage to mathematical probability. Weber's death was not heroic in traditional terms. There was no final combat, no opportunity for defiance, just mechanical destruction delivered with industrial precision. He likely never understood what killed him, never comprehended that radar had detected his aircraft minutes before shells reached him, never realized that his tactical skill was irrelevant against an enemy who fought with information rather than just firepower. For Sergeant Chen, Weber's death was a blip disappearing from a screen, a notation in a log, evidence of system functionality rather than human tragedy. This emotional distance was necessary for continuous operations. Radar operators processed hundreds of targets per shift, many of which represented enemy aircraft being engaged by Allied forces. Dwelling on the human implications of each radar contact would make the work psychologically unbearable. The technology mediated between operator and consequence, creating psychological separation that allowed the work to continue. Chen knew intellectually that radar contacts represented human beings in aircraft, that destroyed contacts meant people dying, but the cathode ray tube's abstract representation made those deaths feel less immediate than they were. This psychological dynamic, technology enabling killing while creating emotional distance from consequences, characterized modern warfare in ways that troubled some observers and seemed merely pragmatic to others. The radar operator killed more efficiently than the rifleman, directed lethal force with greater precision than the artillery observer, and participated in deaths far exceeding what individual direct combat could achieve, yet did so from positions of relative safety and emotional remove. Whether this represented moral progress, moral degradation, or merely inevitable technological evolution remained debated, but its practical military significance was undeniable. The side with superior information technology could kill more effectively while suffering fewer casualties. As the war in Europe approached its conclusion in spring 1945, American radar dominance became increasingly decisive. The Luftwaffe, already crippled by fuel shortages, pilot attrition, and overwhelming numerical inferiority, found itself unable to operate effectively in airspace where every movement was detected, tracked, and engaged. German ground forces, subjected to systematic air interdiction enabled by radar-directed operations, could not maneuver or concentrate without being observed and attacked. The Wehrmacht's final defensive campaigns occurred under skies that were transparent to Allied observation and opaque to German forces, a fundamental asymmetry that no amount of tactical skill or battlefield courage could overcome. The Allied victory, when it came, resulted from many factors: industrial capacity, manpower, strategic decisions, tactical execution, and the moral bankruptcy of the Nazi regime that drove resistance long past rational calculation. But woven through all these factors was the technological superiority that American radar represented, the systematic information dominance that made visible what enemies could not see, that enabled coordination enemies could not achieve, and that translated scientific knowledge into military advantage through institutional competence and industrial capacity. The radar installations humming across liberated Europe were not just technical equipment, but physical embodiments of the systematic advantages that democratic industrial societies possessed over authoritarian regimes, whose institutional dysfunctions prevented them from competing in domains where success required genuine scientific excellence, technical competence, and organizational effectiveness. In the post-war decades, as veterans reflected on their experiences and historians analyzed the war's conduct, radar's decisive role became increasingly recognized. The MIT Radiation Laboratory's work was declassified, revealing the scope and sophistication of American radar development. Technical histories documented how radar enabled strategic bombing, facilitated amphibious operations, revolutionized naval warfare, and transformed air defense. The SCR-584 and other American radar systems were studied as exemplars of applied science, of research institutions successfully translating laboratory innovations into operational military capabilities, and of technological development's proper relationship with military doctrine. German post-war assessments acknowledged radar's decisive impact. Luftwaffe veterans recognized that they had fought an enemy who possessed systematic information superiority that nullified German tactical advantages. Military historians documented how radar-directed air defense had made daylight operations increasingly costly, how night operations had become possible for Allied forces while remaining hazardous for Germans, and how the technological gap had widened rather than narrowed as the war progressed. The lesson was clear. Modern warfare required technological sophistication that only societies with functional scientific institutions, advanced industrial capacity, and effective organizational structures could achieve. The SCR-584 radar that Sergeant Chen operated on that February afternoon became a museum piece after the war, preserved as an artifact of technological history and military innovation. Visitors could observe the equipment, read descriptions of its capabilities, and learn about its operational employment. But the preserved hardware could not convey the psychological impact of the technology, the way it transformed warfare by making invisible dimensions visible, the asymmetry it created between those who possessed it and those who faced it without equivalent capability. The museum radar was silent, its cathode ray tube dark, its antenna stationary, its hum extinct. The living technology had been something different, had been power projecting through electromagnetic spectrum, had been industrial capacity manifesting as information dominance, had been the sound and sight of American technological civilization overwhelming enemies who could not match its systematic advantages. Oberleutnant Weber's name appears in Luftwaffe casualty records as killed in action on February 22, 1945, his FW-190 shot down by anti-aircraft fire east of Aachen. The notation is brief, clinical, providing no details about how or why he died, offering no insight into whether he suffered or died instantly, recording only the fact of death and the general circumstances. His family received notification through official channels, learned that he had died in combat, and presumably mourned a son and brother lost to war's violence. They likely never knew about the radar that had detected his aircraft, the computer that had calculated firing solutions, the anti-aircraft battery that had executed the mission, or the American sergeant who had watched a phosphorescent blip disappear from a screen. The technological architecture of Weber's death remained invisible to those who grieved him, just as it had been invisible to Weber himself. Sergeant Chen survived the war, returned to civilian life in California, and worked for aerospace companies developing the next generation of radar and electronic systems. His wartime service remained largely private. He spoke little about his experiences, maintained contact with some fellow veterans, and carried memories that resisted articulation. How does one explain sitting in a radar van watching aircraft die as abstract traces on a screen? How does one convey the strange combination of boredom and responsibility, the routine of continuous operations punctuated by moments of acute importance, the knowledge that information you provided enabled killing yet feeling emotionally distant from those deaths? Chen found that most people could not understand that the experience existed beyond conventional language, and that silence often seemed more honest than explanation. The technological legacy of wartime radar development extended far beyond military applications. Post-war radar enabled civilian aviation, weather forecasting, space exploration, and countless other domains, where remote sensing and information systems provided capabilities previously unimaginable. The MIT Radiation Laboratory's research produced not just military hardware, but fundamental advances in microwave engineering, signal processing, and systems integration that shaped electronics development for decades. The expertise developed during the war migrated to civilian industry, universities, and research institutions, accelerating technological progress in directions that wartime development had opened. But the fundamental lesson remained military and strategic. Information dominance matters as much as firepower. Technological superiority creates asymmetries that tactical skill cannot overcome, and societies capable of systematic innovation possess advantages that authoritarian regimes cannot match. The radar installations that hummed across Europe in 1945 were not just detecting aircraft, they were revealing fundamental truths about how industrial democracies could compete against and ultimately defeat totalitarian alternatives, how scientific knowledge properly organized and supported could translate into decisive military advantage, and how the invisible dimensions of electromagnetic spectrum could become battle space as important as land, sea, or air. The sound of that radar installation, the hum that Sergeant Chen heard through his headphones and that vibrated through frozen German soil, persists in historical memory not as audio recording, but as metaphor for technological dominance and asymmetric advantage. It was the sound of American industrial might converting raw materials into sophisticated electronics, of scientific research transforming laboratory curiosities into operational systems, of institutional competence maintaining complex technology under combat conditions, and of systematic innovation creating capabilities that enemies could neither match nor effectively counter. Most fundamentally, it was the sound of information itself, electromagnetic pulses traveling at light speed, reflecting from distant targets, returning with data that transformed invisible sky into transparent battle space. In the post-war world that emerged from Allied victory, radar became foundational infrastructure rather than exotic technology. Every airport, every weather station, every ship and aircraft, every military installation all depended on radar systems that descended from wartime development. The technology became so ubiquitous that its revolutionary nature faded from consciousness, its presence accepted as natural rather than recognized as the product of specific historical innovations under wartime pressures. But for those who understood history, who recognized the technological arc from experimental pre-war systems to the sophisticated networks that dominated European skies in 1945, radar remained exemplar of how scientific knowledge, industrial capacity, and institutional competence combined to create decisive military advantages. The frozen ground east of Aachen, where that radar installation operated in February 1945, has changed beyond recognition. The forests have grown, roads have been built, and the specific location where Sergeant Chen watched his cathode ray tube has been absorbed into post-war development. No marker indicates where the radar sat, no memorial acknowledges the deaths it enabled, no physical trace remains of the technology that operated there. But in military museums and technical archives, in veterans' memories and historical accounts, in the broader story of how World War II was fought and won, that radar installation persists as representative of larger truths about technological warfare and the systematic advantages that American industrial civilization could generate when fully mobilized. Oberleutnant Weber's death and the deaths of thousands of other skilled pilots who died without understanding what killed them stand as testimony to how technological asymmetry shapes warfare's human cost. They were not defeated by superior courage, were not outfought in fair combat, but were instead overwhelmed by enemies who possessed systematic advantages that made traditional tactical skill increasingly irrelevant. Their training, experience, and individual excellence were nullified by technology they could not detect, could not understand, and could not effectively counter. They fought bravely according to doctrines developed over decades of aerial warfare, but those doctrines had become obsolete the moment radar made the sky transparent to one side while remaining opaque to the other. The hum of radar installations across Europe in 1945 was the sound of that obsolescence, the audio signature of information dominance rendering traditional combat skills insufficient for survival. It was the sound of modern warfare's transformation from tests of individual skill and unit coordination to systematic application of technological superiority. It was the sound of American industrial civilization, with its functional research institutions, effective organization structures, and massive productive capacity, demonstrating advantages that authoritarian alternatives could not match. And it was the sound of the future arriving in ways that combatants could not fully comprehend, a future where information would be as valuable as ammunition, where seeing the enemy first would matter more than shooting accurately, and where the invisible electromagnetic spectrum would become battle space as contested and decisive as any physical terrain. That hum continued long after World War II ended, evolved and transformed, but fundamentally recognizable, as radar technology developed through Cold War confrontations, regional conflicts, and the continuous technological competition that characterized military affairs. It persists today in the electronic systems that make modern warfare possible, in the sensors and networks that create information dominance, in the technological asymmetries that separate military powers from military weakness. The specific technology has changed. Solid-state electronics replaced vacuum tubes, digital processing replaced analog computers, sophisticated software replaced mechanical calculations, but the fundamental principle remains unchanged. Those who can see the battlefield more clearly, who possess systematic information superiority, who maintain technological advantages that enemies cannot match or counter, will prevail regardless of the enemy's courage, skill, or determination. The Germans never knew about that hidden radar controlling the skies, at least not in time to counter it effectively. They died without comprehending what killed them, fought according to doctrines that had become obsolete, and persisted in resistance long past the point where technological inferiority made defeat inevitable. Their ignorance was not stupidity, but systematic disadvantage. They lacked the institutions, resources, and organizational competence to compete in domains where American advantages were overwhelming. The radar that hummed in camouflaged installations across Europe was not just technical equipment, but physical manifestation of why democratic industrial societies, when fully mobilized and properly organized, possessed advantages that authoritarian alternatives could not overcome. That hum, barely audible to those nearby and completely inaudible to enemies being tracked, was the sound of power projecting through invisible dimensions, the voice of technological dominance that changed warfare forever, and the requiem for all those who died because they fought an enemy they could not see, understand, or effectively resist.